When you blast a mass of enclosed air with intense heat, the gas particles speed up, collide with incredible force, and demand more space. As the gas expands, the density drops, and thousands of pounds of canvas and wicker are carried directly into the sky. But thermodynamics works in both directions. If you take an inflated balloon and leave it inside a cold refrigerator, cooling those exact same gas particles causes them to slow down and pull closer together. The balloon noticeably shrinks. These opposing reactions are governed by Charles's law. It dictates that as long as pressure remains constant, the volume of a fixed mass of gas is strictly proportional to its absolute temperature. We can translate that physical behavior into exact numbers. I'm going to walk you through a clear 4-step framework that will help you solve any Charles's law word problem flawlessly. To follow along, you'll need to grab a calculator, a pen, and some paper. Once you learn this process, you are gaining the ability to accurately calculate and predict exactly how a gas will behave under thermal stress. Step 1 is extracting your data. Let's start with a classic problem. A gas occupies 2.0 liters at 300 Kelvin. What will be its volume at 450 Kelvin if the pressure remains constant? Instead of keeping those numbers floating in your head, draw a simple 2x2 grid to separate the initial state of the gas from its final state. We scan our problem for the first known variable. The gas starts out taking up 2.0 liters of space, so that becomes our initial volume, or V1. At that exact moment, the gas is sitting at 300 Kelvin. We drop that right below into the initial temperature box, T1. The problem then tells us the gas is heated to 450 Kelvin. That is our final temperature, T2. We leave the final volume, V2, marked with a question mark, because that is our target. Visually locking in your variables like this before you do any algebra ensures you never place the wrong number into the final equation. Step 2 is avoiding a frequent calculation error known as the Celsius trap. Gas laws must be calculated using the absolute temperature scale. Absolute zero is the theoretical point where gas particles have zero kinetic energy, which lands at negative 273.15 degrees Celsius. If you plug negative Celsius numbers into a gas law formula, you will end up calculating a negative volume, which is physically impossible. To prevent this, you must convert any Celsius temperature to Kelvin by adding 273.15. Looking back at our extracted variables, both of our temperatures are already cleanly stated in Kelvin. We are cleared to move to the math. If your problem gives you Celsius, your process halts immediately until that conversion is done. Step 3 is execution. The mathematical expression of Charles's law states that V1 divided by T1 equals V2 divided by T2. We take our locked-in grid and substitute the values directly into the formula. That gives us 2.0 over 300 on the left, equal to our unknown V2 over 450 on the right. Double-check your layout here. A common mistake is accidentally swapping a final state variable over to the initial side. Step 4 is isolation. We need to get V2 entirely by itself, and the cleanest way to do that is through cross-multiplication. We multiply the numerator of each side by the denominator of the opposite side. We multiply 2.0 by 450 and set it equal to 300 multiplied by V2. Now we just clean up the algebra. Multiplying 2.0 by 450 gives us 900. To isolate V2, we divide both sides by 300. 900 divided by 300 leaves us with a final volume of exactly 3.0 liters. Before you move on, you have to run a quick directional logic check. This ensures your calculation makes sense in the physical world. Our initial temperature went from 300 Kelvin up to 450 Kelvin. Because the temperature increased, Charles's law requires the volume to increase alongside it. This graph plots volume on the y-axis against temperature on the x-axis. As we plot our initial state of 300 Kelvin and 2 liters, and draw a straight line to our final state of 450 Kelvin and 3 liters, we see perfect direct proportionality. By organizing your variables, checking your Kelvin, cross-multiplying, and checking your logic, you guarantee an accurate answer. You've successfully calculated exactly how much that gas needed to expand to maintain its pressure. This exact mathematical principle is happening inside a bakery oven right now. The heat causes the tiny gas bubbles trapped inside the dough to rapidly expand in volume, resulting in a perfectly raised, fluffy loaf of bread. Now it's time to put your own skills to the test. A gas has a volume of 5 liters at 250 Kelvin. What is its volume at 500 Kelvin? Use the 4-step framework to lock in your variables and isolate your unknown. Once you have your final volume, drop your answer down in the comments below.